For decades, we told ourselves a tidy story about Mars. It tried to become another Earth failed, dried up, and died. Simple closed case. But that story just fell apart because NASA and independent research teams have uncovered something buried deep under that rust-colored surface that shouldn't be there. Something vast, intricate, and unnervingly Earth-like. Scientists are now rewriting what they thought they understood about the red planet. And every new piece of evidence pushes the same question, closer to the surface: did something once live there? Let's walk through it piece by piece, because none of these findings are small. They're not footnotes buried in obscure journals. They're the kind of results that redirect an entire field. And the striking part is that they're all surfacing at once, all pointing toward the same unsettling possibility. Start with a paper published June 26, 2026. A team from the University of Oxford, writing in Nature Astronomy, described something extraordinary buried inside Mars. Using seismic readings from NASA's InSight lander, they identified a hidden boundary roughly 24 kilometers, about 15 miles beneath the surface, a depth where Marsquake-generated seismic waves bent and slowed in a way that pointed to a distinct chemical transition. Below that threshold, the rock behaved like an entirely different substance, a thick band of ultramafic rock, the dense material left behind when magma cools slowly and its heaviest minerals settle out. Deeper still, around 38 kilometers down, lies the actual crust-mantle boundary. The data revealed a 14-kilometer thick zone of melt-depleted cumulate rock sitting just above the mantle. Not a minor geological curiosity, but the signature of something much bigger. Lead researcher Dr. Toba Mori-McKay of the University of Bristol put it. Plainly, scientists had long assumed Martian volcanism was fairly basic compared to Earth's, but this find suggests Mars could sustain enormous long-lived magma systems capable of continuously reworking molten rock throughout its crust. Researchers are calling this transcrustal magmatism, and until now this process had only ever been observed on Earth. It's the mechanism behind how Earth builds its layered continental crust. Magma rises from the mantle, pools and reservoirs at various depths, chemically differentiates as it cools and slowly assembles complex evolved rock. It was thought to require plate tectonics, the grinding motion of Earth's crustal plates that drives magma upward and recirculates material over millions of years. Mars has never had plate tectonics, and yet it apparently built the same kind of elaborate magmatic plumbing anyway. The scale is what makes this even stranger. That same 24-kilometer boundary hasn't just been found under the InSight lander orbital surveys, have picked up matching seismic signatures across much of Mars's northern hemisphere. This wasn't a single volcano over a localized hotspot. It looks like a connected web of massive evolving magma chambers spanning much of the planet's interior, potentially active for billions of years. Oxford's official statement noted that this kind of geological process is tied to how planets develop atmospheres, oceans, and habitable conditions on Earth. It helps regulate climate and cycle water and other volatiles. Scientists assumed plate tectonics were a prerequisite for that. Mars just showed they might be wrong. Complex geology and the chemistry needed for habitability can apparently arise without plate tectonics at all. That's a meaningful shift in where else in the universe life might be possible. This magma story connects directly to something uncovered months earlier. In September 2025, NASA announced what it called one of the most significant findings in the history of Mars: exploration. The Perseverance rover, which landed in Jezero Crater in February 2021, had been examining a banded reddish rock nicknamed Chayava Falls after a waterfall in the Grand Canyon. About a meter long and 60 centimeters wide, it looked unremarkable until Perseverance's instruments took a closer look. Scattered across a central band were millimeter-sized, irregular light-colored patches, each ringed by a darker halo dubbed leopard spots. The minerals forming them weren't random vivianite, a hydrated iron phosphate, and gragite, an iron sulfide arranged in a structured repeating pattern. In their peer-reviewed findings, NASA's team described the spots as chemical reaction fronts, sites of ancient oxidation reduction chemistry. On Earth, those same reactions are often driven by microbial activity. Vivianite typically forms where organic matter is decaying. Gragite is commonly produced by sulfate-consuming microbes. The concentric structured pattern of the two together is the kind of arrangement planetary scientists associate with biosignatures. Nicola Fox, then head of NASA's Science Mission Directorate, said publicly, "This was the closest the agency had ever come to finding evidence of ancient Martian life, a striking statement from someone in that position." To be clear, scientists aren't calling it proof. They call it a potential biosignature and have worked hard to rule out non-biological explanations. A September 2025 study in Nature tested various purely geological alternatives and found none of them held up particularly well. The biological explanation remains unconfirmed, but it's the cleanest fit for what's been observed. Then, in June 2026, a follow-up study in Science Advances found macromolecular carbon MMC, large complex carbon networks in rocks, from the nearby Bright Angel Formation, right next to where Chayava Falls was found. On Earth, MMC shows up mainly in rocks with fossilized biological carbon, or in meteorites. Researchers called the detection an unambiguous confirmation of organics on Mars. Crucially, it's not scattered randomly, it's concentrated in rocks, from what was once an ancient lake bed in a clay-rich layer that only forms in the presence of water. Put together, an ancient lake, water-formed clay, minerals complex, organic carbon, mineral patterns that resemble microbial chemistry on Earth. And as the newest research shows, a subsurface once threaded with active magma systems that could have supplied the heat to keep underground water liquid for billions of years. That brings us to the discovery that ties everything together. In 2024, researchers studying InSight seismic data found that somewhere between 7, 1, and 12, 4 miles beneath the surface, seismic waves were slowing in a pattern consistent with liquid water, trapped in porous rock, essentially an aquifer similar to ones on Earth. The reservoir is large enough that if spread evenly across the planet, it could form a global ocean between half a mile and over a mile deep. Teams at Australian National University and the Chinese Academy of Sciences later corroborated the finding using separate seismic datasets, and in March 2026, researchers from NYU Abu Dhabi, publishing in the Journal of Geophysical Research, confirmed that ancient dunes in Gale Crater had been cemented by groundwater, flowing through them long after Mars's surface lakes and rivers had already vanished, meaning the underground water system persisted far longer than expected. Together, these findings rewrite the old narrative Mars didn't simply dry out and die. Its water moved. As the surface cooled and the atmosphere thinned past the point where liquid water could survive above ground, billions of years' worth of water likely drained downward through cracks left by early intense meteorite bombardment. Deep enough underground, residual heat from the planet's interior kept it liquid, and seismic data suggests a substantial portion may still be liquid, today sitting in a vast, dark aquifer 7 to 12 miles beneath the surface. The astrobiological implications here are enormous. On Earth, microbes live in rock fractures, miles underground in total darkness. At extreme pressure, entirely cut off from the surface. Organisms first discovered in South African gold mines more than 2 kilometers down, they survive on radiolytic hydrogen produced when natural radiation splits water molecules into hydrogen and oxygen. The hydrogen becomes their food source. These communities can persist in isolation for potentially millions of years. If Mars has a comparable aquifer 712 miles down, and its rocks contain radioactive elements, which they demonstrably do, the same chemical conditions that sustain deep subsurface life on Earth could exist on Mars right now, not just in its ancient past. NASA scientists have said this discovery effectively shifts the search for Martian life from the surface to the deep subsurface. The surface itself is brutal, blasted by cosmic radiation swinging hundreds of degrees between day and night with no liquid water and no protective magnetic field. Mars does have a layered core, a solid inner core, wrapped in a liquid metallic outer layer, structurally similar to Earth's. The key difference is that Mars' liquid outer core no longer circulates fast enough to generate a magnetic field that internal motion stalled billions of years ago. Once it did, Mars lost its magnetic shield. Its atmosphere gradually escaped into space and surface water, either evaporated or froze. But earlier in its history, while it still had that magnetic field, Mars also had a thicker atmosphere and enough surface pressure to keep liquid water stable above ground. The evidence is everywhere dry. Riverbeds, ancient lake sediments, and outflow channels carved by what must have been catastrophic floods. Jezero Crater, where Perseverance operates today, was once a lake fed by rivers. During that period, Mars had liquid surface, water warmth from active volcanism. The same transcrustal magma systems the 2026 Oxford study revealed ongoing geological activity, generating new minerals and energy sources, and a magnetic field shielding the surface from radiation. By every standard planetary scientists use, early Mars was genuinely habitable, not marginally, not arguably, but habitable by definition. More recently, Perseverance turned its laser spectrometer on pale rocks in Jezero Crater and detected microscopic grains of corundum, the mineral behind rubies and sapphires, in results presented at the 2026 Lunar and Planetary Science Conference. The surprise isn't monetary value, it's that corundum needs very specific conditions to form high aluminum, low silicon, and typically either extreme heat or tectonic activity, neither of which should apply easily to Mars. Yet there, it was confirmed by laser spectroscopy. Something about that. Locations. Ancient chemistry was exotic enough to produce it. Another reminder that Mars keeps revealing chapters. nobody expected. Step back and look at the whole picture. An interconnected magma system that may have run through Mars' crust for billions of years, something previously thought unique to Earth. Ancient surface water that once filled lakes and craters like Jezero A layered core structures similar to Earth's. A present-day aquifer based on seismic data sitting 712 miles underground and potentially large enough to cover the planet in an ocean up to a mile deep. A rock Chiava Falls bearing mineral patterns that on Earth are specifically tied to microbial chemistry, with every purely geological explanation falling short. Complex organic carbon molecules confirmed right next to those same patterns. A planet that didn't lose its water so much as hide it underground where it may remain today. The old narrative cast Mars as Earth's tragic neighbor, a world that almost made it too small to hold an atmosphere, too cold to keep water too geologically simple for the complexity life requires dead frozen. Bearing worth a bit of sympathy for having tried. That story doesn't hold up anymore. What the 2025 Tuno Totu 6 data actually describes is a planet that built Earth-like geology without Earth's usual tools, and that kept its water even after losing everything else by moving it into a hidden underground reservoir that may still exist. The most promising place to look for life in the solar system beyond Earth might not be any surface at all. It might be a dark, wet, chemically active layer of rock several miles down, warmed just enough by the planet's own residual heat, shielded from radiation by miles of overlying rock, and chemically active enough to generate usable energy. The question isn't really was Mars ever habitable anymore that's essentially settled. It was, the live question now is whether anything that started there ever stopped, whether life, if it existed, retreated from a warming then cooling surface into that underground refuge, and whether something down there sealed off from the universe above for billions of years might still be quietly surviving on hydrogen. In the dark, we can't answer that. Yet drilling technology capable of reaching 712 miles into Martian rock doesn't exist. The Mars Sample Return Mission, which would bring Perseverance's collected samples including Chiava Falls back to Earth for full lab analysis, is facing serious funding uncertainty. China's Tianwen-3 Sample Return Mission is aimed at a different, less geologically compelling site and isn't due until later this decade. The evidence is out there already collected, in some cases sitting in rock samples on a planet 140 million miles away. Getting it home or getting instruments deep enough is the remaining challenge. This isn't a single finding. It's 5 or 6 independent discoveries published within months of one another, all converging on the same conclusion: a planet far more geologically active than assumed, one that hid its water rather than losing it with rock chemistry that echoes the fingerprints of biological processes, and a core history that explains why the surface died even as the interior may have stayed active. Consider the pace over just the past year. September 2025, NASA's head of science publicly calls the Chiava Falls leopard, spots the closest the agency has come to finding evidence of ancient Martian life. Late 2025. A peer-reviewed Nature paper confirms Mars's solid inner core, settling a long-running debate. Early 2026 studies confirm groundwater persisted beneath Gale Crater long after surface lakes disappeared. March 2026, NYU. Abu Dhabi research extends the estimated timeline of active Martian subsurface water further than previously thought, June 2026. Complex organic carbon confirmed near the Leopard Spot site, June 2026. The Oxford team publishes evidence of Earth-like transcrustal magma systems, potentially spanning thousands of kilometers across Mars's northern hemisphere. Any single one of these would normally be a major scientific event on its own, 6 of them landing within a year, all pointing at the same planet and the same underlying story is something different entirely. If samples from Jezero Crater are ever returned and analyzed, and if they reveal genuine fossilized biosignatures, or if the deep aquifer is eventually reached and found to host microbial life, the implications would extend well beyond planetary science into philosophy, into how common life might be throughout the universe, and into the Fermi paradox, the long-standing puzzle of why we haven't detected intelligent life given how vast and old the universe is. If life arose independently on 2 neighboring worlds in the same solar system that would suggest it isn't rare at all, it might be common.